Hello, friends. In our earlier discussion, we learned that the kinetic theory of gases relates the macroscopic properties of gases to the microscopic properties of gas molecules. An ideal gas is one for which the pressure, volume, and temperature are related by the ideal gas law, and the pressure of the gas, a purely macroscopic quantity, depends on the speed of the molecules, a purely microscopic quantity. In today's lecture, we shall be discussing what is meant by mean free path. Apply the relationship between mean free path, the diameter of molecules, and the number of molecules per unit volume. Explain how Maxwell's speed distribution law is used to find the fraction of molecules with speeds in a certain speed range. Sketch a graph of Maxwell's speed distribution. Explain how Maxwell's speed distribution is used to find the average speed, the RMS speed, and the most probable speed. Mean free path. We here examine the motion of molecules in an ideal gas. Figure shows the path of a typical molecule as it moves through the gas, changing both speed and direction abruptly as it collides elastically with other molecules. Between collisions, the molecule moves in a straight line at constant speed. Although the figure shows the other molecules as stationary, they are, of course, also moving. One useful parameter to describe this random motion is the mean free path lambda of the molecules. As its name implies, lambda is the average distance traversed by a molecule between collisions. We expect lambda to vary inversely with the number of molecules per unit volume or density of molecules. The larger the density is, the more collisions there should be, and the smaller the mean free path. We also expect lambda to vary inversely with the size of the molecules, with their diameter. If the molecules were points, as we have assumed them to be, they would never collide and the mean free path would be infinite. Thus, the larger the molecules are, the smaller the mean free path. We can even predict that lambda should vary inversely as the square of the molecular diameter because the cross section of a molecule, not its diameter, determines its effective target area. The expression for the mean free path does, in fact, turn out to be lambda is equal to 1 upon under root 2 pi d square n upon v. Here, n upon v is the number of molecules per unit volume, d is the diameter. To justify this equation, we focus attention on a single molecule and assume, as the figure suggests, that our molecule is traveling with a constant speed v and that all the other molecules are at rest. Later, we shall relax this assumption. We assume further that the molecules are spheres of diameter d. A collision will then take place if the centers of two molecules come within a distance d of each other, as in figure A. Another more helpful way to look at this situation is to consider our single molecule to have a radius of d and all the other molecules to be points, as in figure B. This does not change our criteria for collision. As our single molecule zigzags through the gas, it sweeps out a short cylinder of cross-sectional area pi d square between successive collisions. If we watch this molecule for a time interval delta t, it moves a distance v delta t, where v is its assumed speed. Thus, if we align all the short cylinders swept out in interval delta t, we form a composite cylinder of length v delta t and volume pi t square into v delta t. The number of collisions that occur in time t is then equal to the number of point, or we should say molecules, that lie within this cylinder. Since n upon v is the number of molecules per unit volume, the number of molecules in the cylinder is nv times the volume of the cylinder, or pi d square v delta t into n upon v. This is also the number of collisions in time delta t. The mean free path is the length of the path and of the cylinder divided by this number, that is, lambda is equal to length of the path during delta t divided by number of collisions in delta t, and is approximately equal to v delta t divided by pi d square v delta t into n upon v, which is equal to 1 upon pi d square into n upon v. This equation is only approximate because it is based on the assumption that all the molecules except one are at rest. In fact, all the molecules are moving. When this is taken properly into account, equation A results. Note that it differs from the approximate equation only by a factor of 1 upon under root 2. The approximation in equation A involves the two V symbols we cancelled. The V in the numerator is V average, the mean speed of the molecules relative to the container. The V in the denominator is V relevant, the mean speed of our single molecule relative to the other molecules which are moving. It is this latter average speed that determines the number of collisions. A detailed calculation taking into account the actual speed distribution of the molecules gives V relative is equal to under root 2 into V average, and thus the factor under root 2. The distribution of molecular speeds. The objective here is to explain how Maxwell's speed distribution law is used to find the fraction of molecules with speeds in a certain speed range. The second objective is to sketch a graph of Maxwell's speed distribution, showing the probability distribution versus speed and indicating the relative positions of the average speed, the most probable speed, and the RMS speed. Then we are to explain how Maxwell's speed distribution is used to find the average speed, the RMS speed, and the most probable speed. The root mean square speed gives us a general idea of molecular speeds in a gas at a given temperature. We often want to know more. For example, what fraction of the molecules have speeds greater than the RMS value? What fraction have speeds greater than twice the RMS value? To answer such questions, we need to know how the possible values of speed are distributed among the molecules. Figure here shows the distribution for oxygen molecules at room temperature, that is T is equal to 300 Kelvin. And this figure compares it with the distribution at T is equal to 80 Kelvin. In 1952, Scottish physicist James Clerk Maxwell, first solved the problem of finding the speed distribution of gas molecules. His result, known as Maxwell's speed distribution law, and is given by this equation. Here, m is the molar mass of the gas, r is the gas constant, T is the gas temperature, and V is the molecular speed. It is this equation that is plotted in the two figures. The quantity PV in equation and figures is a probability distribution function. For any speed V, the product PV into dV, a dimensionless quantity, is the fraction of molecules with speeds in the interval dV centered on speed V. As the first figure shows, this fraction is equal to the area of a strip with height PV and width dV. The total area under the distribution curve corresponds to the fraction of the molecules whose speeds lie between 0 and infinity. All molecules fall into this category, so the value of this total area is unity, that is, integral of PV into dV from 0 to infinity is equal to 1. The fraction of molecules with speeds in an interval of, say, V1 to V2 is then equal to integral of PV into dV from V1 to V2. Average, RMS, and most probable speeds. In principle, we can find the average speed of the molecules in a gas by weighing each value of V in the distribution. That is, we multiply it by the fraction PV/dV of molecules with speeds in a differential interval dV centered on V. Then we add up all these values of V into PV/dV. The result is V average. In practice, we do all this by evaluating integral of V PV into dV from 0 to infinity. Substituting for PV from Maxwell's speed distribution law and using generic integral, we find V average is equal to under root of 8 RT upon pi m. Similarly, we can find the average of the square of speeds v square average with v square average is equal to integral of v square pv dv from 0 to infinity. Substituting for pv from Maxwell's speed distribution law and using generic integral, we find v square average is equal to 3RT upon m. The square root of v square average is the root mean square speed Vrms. Thus, Vrms is equal to under root of 3RT upon m. The most probable speed Vp is the speed at which Pv is maximum. To calculate Vp, we set dp upon dv is equal to 0. As you can see, the slope of the curve in figure is 0 at the maximum of the curve, and then solve for v. Doing so, we find Vp is equal to under root of 2RT upon m. A molecule is more likely to have speed Vp than any other speed, but some molecules will have speeds that are many times Vp. These molecules lie in the high speed tail of a distribution curve. Such higher speed molecules make possible both rain and sunshine, without which we could not exist. The speed distribution of water molecules in, say, a pond at summertime temperatures can be represented by a curve similar to that as shown in this figure. Most of the molecules lack the energy to escape from the surface. However, a few of the molecules in the high speed tail of the curve can do so. It is these water molecules that evaporate, making clouds and rain possible. As the fast water molecules leave the surface, carrying energy with them, the temperature of the remaining water is maintained by heat transfer from the surroundings. Other fast molecules produced in particularly favorable collisions quickly take the place of those that have left, and the speed distribution is maintained. Sample problem. If the molar mass m of oxygen is 0.0320 kg per mole, find out what is the average speed V average of oxygen gas molecule at T is equal to 300 Kelvin. Second, what is the root mean square speed VRMS at 300 Kelvin? And what is the most probable speed Vp at 300 Kelvin? To find the average speed, we must weight speed v with the distribution function Pv of Maxwell's speed distribution law and then integrate the resulting expression over the range of possible speeds, that is, from 0 to the limit of an infinite speed. So we end up with this equation: V average is equal to under root of 8 RT upon pi m. Substituting the values, we get V average is equal to 445 meters per second. The result is plotted in this figure here. To find VRMS, we must find V square average by weighting V square with the distribution function Pv of Maxwell's speed distribution law and then integrating the expression over the range of possible speeds. After taking the square root of the result, we end up with this equation: Vrms is equal to under root 3 RT upon m, and substituting the values we find Vrms is equal to 483 meters per second. This result, plotted in figure, is greater than V average because the greater speed values influence the calculation more when we integrate the V square values than when we integrate the V values. The most probable speed. Speed Vp corresponds to the maximum of the distribution function Pv, which we obtain by setting the derivative dp upon dv equal to 0 and then solving the result for v. We find Vp is equal to under root of 2 RT upon m. Substituting the values, we find Vp is equal to 395 meters per second. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. The mean free path of a gas molecule is the average path length between collisions. Maxwell distribution describes particle speeds in gases, where the particles move freely without interacting with one another, except for very brief elastic collisions in which they may exchange momentum and kinetic energy, but do not change their respective states of intramolecular excitation as a function of the temperature of the system, the mass of the particle, and speed of the particle. So that is it for today. In the next lecture, we shall be discussing about molar specific heats of ideal gas. Thank you very much.